All right. Hello. Welcome to Astronomy on Tap. I'm Andy Howell. This is Yair Erkavi.
Hello.
We'll be hosting tonight, and the plan for tonight is first we're going to talk to Sally Shaw, who's going to tell us about experiments looking for dark matter. And then we will have a 5-minute break, and then we'll answer your questions. Text your questions to 805-55-AOT-SB. You can look at it on the board right over here. If you type on your iPhone, you can just type the actual letters. You don't even, or your whatever kind of phone. You don't have to know the numbers that correspond. And it will get to us. We'll pick out the best questions and ask her after the break. Then we'll do astronomy in the news. Then another 5-minute break. And then we'll have Brian and Eric tell us about Las Cumbres Observatory and how the infrastructure of that works and the whole history of the observatory. And then we'll say, text your questions again to the same number. Then we'll have upcoming events, answers to questions, and then a raffle at the end.
Right, and if we pick your question on stage, please see Sandy in the back and you'll get a free Las Cumbres Observatory postcard of this beautiful galaxy M83. Okay, also in the front desk, we rely on your help to keep Astronomy on Tap going. It's a fully voluntary event and we want to keep it free for everyone, so we are grateful if you want to help us out. And if you want to help us out to the amount of $10, you'll get a nice AOT t-shirt, and I see some people in the audience wearing their t-shirts, and that's great. And for $20, one of our unique Las Cumbres Observatory posters of these different space objects. And we are, I think a few of them are already gone, so we have a few left. And also, feel free to just say hello at the front desk. And a pen, free Astronomy on Tap pen or magnet or both, just for coming here tonight. So, yes, thank you very much. Okay, so we're going to get started, and our first speaker today is Sally Shaw. She's a postdoc at UCSB, and she is a physicist, a particle physicist, okay? But she's a nice person. Okay, so why is a particle physicist talking in Astronomy on Tap? So she works on dark matter, and actually dark matter is a really interesting phenomenon, not just in itself, but also in the kind of sociology that has developed around it. So, until now, astronomers have been looking further and further out into the universe, and particle physicists have been drilling further and further down into smaller and smaller scales. And it looked like we were, studying quite opposite things in science. But at some point, the particle physicists started realizing that, hey, maybe we're astronomers are doing something quite interesting when we discover dark matter. And so they started paying attention to our discoveries and trying to coming to our conferences, and we started to go to their conferences. And now this is a really interesting phenomena around which, the particle physicists who are studying the smallest things in the universe and astronomers starting the largest things came together to try and understand this mystery, which Sally's going to tell you more about. So this is how physicists and astronomers came together around this. And so Sally started out in the right direction. This is her at age 11 with a telescope. But then she went, literally to the dark side, I guess. And so I just wanted to show you, when we were rehearsing this talk, I couldn't help notice her laptop. She apparently has a thing for pink. So her laptop is entirely pink, including the keyboard. I didn't even know you could do that, as you can see here. Okay, so please welcome Sally.
Okay. Hi, everyone. So I'm Sally. I'm going to tell you as much as I can about the dark matter mystery and what we're actually trying to do here on Earth, especially what we're doing at UCSB, to try and solve that mystery. So, as this is Astronomy on Tap, I'm going to start with talking about our universe. And this is kind of sums up what we know about the universe today. And basically, we think the universe began with the Big Bang, sort of 13.8 billion years ago, where it sort of started from a singularity and expanded outwards, and everything sort of came from then. We had sort of stars formed, galaxies formed, etc. And today, we can sort of measure what the universe is made of by using observations of this very important thing that happened about 375,000 years after the Big Bang, where the universe became transparent to light. And this means that sort of photons, which are particles of light, came sort of streaming outwards at that point. The universe was transparent, they all came out, and we can still measure them today here on Earth with sort of telescopes. That we can use that information to tell us something about what the universe is actually made of. And when we actually sort of do this analysis and work out what our universe is composed of, we get this pie chart here, as you can see. And what's actually a very embarrassing thing for physicists is that we only understand what's going on in that little green segment at the top there with the less than 5% of the universe. So what that means is, as particle physicists, we understand that very well. We have the standard model of particle physics where we have protons and neutrons and electrons and photons, which are particles of light, and we understand those to very high precision. But that overall in our universe is less than 5%. So the rest of it is just a complete mystery to us. And that's kind of, like I say, it's very embarrassing. But we're really trying very hard to understand. And I actually won't be talking about the dark energy side of things very much today, because you have to realize a lot of people think that dark energy and dark matter are related, but they're actually, as far as we know, they're not related. The dark energy is sort of this sort of force or energy that's causing our universe to grow even further. So the universe has been expanding all this time, since the Big Bang, but it's actually starting to speed up its expansion. And we think this is down to something that we call dark energy, because we don't know what it is. It's just some energy that forces things further apart. But I won't be talking about that today. We're actually going to focus on the smaller elephant in the room, which is the dark matter. So that's like 27% of our universe is made up of dark matter. And if you actually weigh things, so if you actually talk about the mass in our universe, dark matter makes up 80% of the sort of heavy stuff that we can, measure out in space. And so that's a really big amount of stuff that we just don't really know what it is at all. So how do we know it's there is obviously the obvious question. And it's dark, so it doesn't give out any light. And everything that you see from sort of astronomy, astrophysical observations, everything is to do with measuring light. So measuring these photons, these particles of light, measuring them at different wavelengths, different frequencies from distant galaxies and stuff like that. But with the dark matter, we can't measure any light from it because it just doesn't give out any light. So we have to measure it in a different way, and we actually use its sort of gravity. So you all know about gravity. It's what holds us onto the Earth. And the first observations of dark matter were sort of in the 1930s, where astronomers were looking through their telescopes, they were looking at galaxies, and they were observing how the galaxies were moving. And what they actually noticed is that galaxies, they all rotate, and this is to do with sort of physical laws and conservation of angular momentum when these things form, but they all spin. And when you sort of measure their rotation, so this is what we actually expect. So we expect that the center of the galaxy actually moves a lot faster than the outside of the galaxy. And this is down to basically how much mass it has within sort of each radius as you move outwards, and how much sort of heavy matter there is, like stars and gas and dust holding things together. And you should actually observe that the outside moves slower than the inside. But this is actually what we measure in every single galaxy. This isn't just a few galaxies, this is all of them. And we notice that the outside moves just as fast as the inside. So this is very strange. And a lot of people, there's still people today that believe that we just have physics wrong. And we just don't understand our sort of laws of motion, Newton's laws of motion, the basic stuff. But, we do, we really do. And we know that because these galaxies are moving so fast around the outside, that this must mean, to hold them together, to allow them to rotate so quickly, there must be more mass that we can actually see. Because if we add up all the mass that's giving out light, it doesn't make any sense. Things should just be flying off into space if these things are moving that quickly. So what we think happens is that there is this something called a dark matter halo in every galaxy, which is sort of a big spherical sort of distribution of dark matter, which is just something that has mass, something heavy, and it holds everything together, so it can all spin very, very quickly. So that's what we sort of believe. And as I say, a lot of people think we might have this wrong, but there are other observations that tell us that we really do have this mysterious heavy stuff out there. And this is kind of one of the key observations that we've made in physics. This is what I mentioned before about the sort of leftover radiation from the Big Bang that we managed to measure now. And this is, if you look at this shape, this is kind of looking at the sky surrounding the Earth. And the hot spots are sort of, this is radiation, so this is light, this is photons. And the hot spots are where the temperature was higher, where there was more matter. And the cold, sort of darker spots are where there was less, and it was cooler, and there was less matter. And you can do some very sort of clever analysis of this stuff, and you can look at the patterns in this and sort of work out how much matter there had to be, how much heavy stuff there had to be across the whole universe. And this also tells us that there really had to be this heavy dark matter stuff around. And what it basically did was it started off galaxy formation. So heavy dark matter was just sort of sitting there, and other gas and dust and everything just sort of clustered onto it and formed galaxies. And you really do need it there. Like we this makes sense to us as physicists. So, and then we now actually have some really nice observations. So this is a galaxy cluster. So you can kind of see these bright spots around in this image, and these are actual whole galaxies. So millions and millions of stars. And what you can do with these sort of clusters is you can measure the mass, like how heavy these clusters are, and you can use two different methods. And what these colors are on this image. They're actually false color added, the pink and the blue. And the pink is added from, if we look at how much radiation, how much light this structure is giving out, we can add up the mass from that, and that gives us the pink region. But if we actually, instead of doing that, if we use a different method to analyze how heavy this thing is, we can use what's called gravitational lensing. And this is a method by, you take a very, very bright distant source, like a very, very bright galaxy, really, really far away, behind this thing, and you look at how the light from that bends on its way to Earth, because light actually bends under gravity too. So you know that gravity attracts masses to other masses. We all stay on the Earth. But it can also bend light when it's very strong. And you can look at light from a very distant source, and you can see how it bends around this cluster of galaxies on its way to Earth. And from that, you can determine where the heavy stuff is in this galaxy cluster. And it actually turns out that it's in these two blue lobes, either side of the sort of main area that's giving out radiation. And again, this tells us that there's something in there that's very heavy, that doesn't give out light, and that's actually just sort of, so what we think has happened here is two galaxy clusters have actually come together and collided. And whilst the normal matter is all sort of stuck together in the middle and interacted and stayed together, the dark matter has just kind of sailed on through and passed through, and you can get these two sort of lobes either side. So this is like what's considered sort of a smoking gun for dark matter evidence, and coincidentally it's called the bullet cluster. But it really does say to us that there is this mysterious substance out there in the universe that we just, so far, can't really understand. We just know it's heavy. So as particle physicists, we know that everything in the universe is made of particles. So we're all made of atoms, which are made of protons and neutrons and electrons, and light is basically particles called photons. So we assume, because it's a reasonable assumption to make, that dark matter is also made from particles. And the name of these particles that we've given them as our best candidate for dark matter is the WIMP, or the weakly interacting massive particle. And this is this really is our best candidate right now for dark matter. So we just think that these are really heavy particles that don't really do very much, that they're WIMPs. But we can try and detect them with particle physics experiments. And this is important to us because, whilst we can detect them through astrophysical observations, and we can detect them, from their gravitational interaction out in space, we really want to be able to see them here on Earth in an experiment to really make sure we understand what's going on. So this is kind of like what the LHC did. You might have heard of the Large Hadron Collider at CERN in Switzerland, and they 30 years ago or something, some theorists came up with the idea of the Higgs boson, which is a particle that gives all other particles mass. And you've probably heard of the Higgs boson. It gets in the news a lot. And this is kind of a similar story. We are looking for the particle like those guys looked for the Higgs boson. It took them 30 years. And we're sort of reaching that limit now from when this was first proposed. But we still haven't found it yet. But we're still looking. But I'm going to tell you there's three kind of ways to look for it in particle physics. And they are known as sort of the production method, the indirect detection, and the direct detection, or make it, break it, shake it is the simpler way. So, so when you make it, as its name suggests, you just try and make it in a particle collider, such as the LHC, where you collide protons, and you try and produce dark matter. And the signature in the detector would just be missing energy, because as its name suggests, it's weakly interacting, it doesn't do much, it should just pass out of your detector. So they try and look for it, the LHC, by looking for missing energy. Then you have the indirect method. So these are like telescopes up in space. This is the Fermi-Lat telescope. And this looks for sort of dark matter in distant galaxies annihilating with itself. So all particles can have an antimatter particle where they can sort of come together and cause an annihilation where they produce energy. And you can look for that happening in distant galaxies. And these telescopes are designed to sort of look for unexplained excesses in gamma rays or other sort of exotic particles that could suggest that there's some dark matter interacting off in this distant galaxy. But the actual method that I'll be talking from now on about is the direct detection, or the shake it method, where we actually look for a dark matter particle coming into a detector on Earth and interacting with an atomic nucleus, in our detector on Earth. And what happens is, so we expect the WIMP would come in and knock into an atom, and you would get a recoil of an atomic nucleus. And you need a detector that can kind of identify that that's happened. So we actually can go down 3 different routes for that, which I've tried to sort of display here. So you can either have a material that gives out light when a particle moves through it. So when this happens, you would collect photons or light. You can also try and look for electrons that have been knocked off their atoms, because you've got a collision going on here. So there's energy being sort of transferred. Electrons might get knocked from their atoms, and maybe you can collect those as ionization. Or also you've got heat or phonons, which is basically, if this happens, you have a very small increase in temperature. So if you have a very, very cold detector, you might be able to detect that too. And the kind of idea of this direct detection is that we're really looking for our very own Milky Way dark matter. And we don't really expect it to be moving. It should just be sitting there. But because we're moving around the sun, and the sun is moving around the entire galaxy, like the galactic center, we should see these WIMPs coming towards us in what we call the WIMP wind. So we should be able to detect them because they're passing through us all the time. And if you're drinking a pint right now, there's probably about 1 WIMP in your pint. But you don't need to worry because it doesn't really do anything. So what materials do we use for these sort of detectors? Well, actually, we found that xenon, or xenon as you would call it here, but I'm afraid I'm going to say xenon, is a really good detector for this sort of thing, because it gives out loads of light. So when charged particles, or when particles move through xenon, it gives out light. So you might know this because xenon is used in car headlights and in neon lights and stuff like that, because it gives out light really nicely. And so what we actually do is we make a sophisticated bucket of liquid xenon. So we liquefy the xenon and we put it in a bucket, and then we actually surround it with what's called a photomultiplier tube, which is a light detector. And I actually have one here that's broken. So the casing has been taken off, so you can see all the insides, which is kind of interesting. But basically, we have these things, and we point them at the liquid xenon. So some on the top, like looking down, some on the bottom. And these detect light, and then they multiply it, and they produce a signal that we can read out with our computers and try and analyze. So the idea is to have the liquid xenon and the photomultiplier tubes, and then also we have, this is called a dual phase detector, so we have a layer of gas on top too. So we let some of the xenon become a gas again, and that sort of sits on top, and this allows us to collect 2 different signals. So I'm just going to show you this video to try and demonstrate how this works. So we expect the dark matter particle will come in, knock into a xenon atom, and you get a flash of light, and you can read that out with your PMTs. And then you actually also will knock off some electrons from atoms around that xenon, And they can be pushed up by an electric field. And when they get up to the gas layer, they produce a second signal. So you actually get two signals from one interaction of the dark matter particle. And these two signals actually are very useful for being able to tell exactly where in the detector this interaction happened. So you can use, so we have hundreds of these photomultiplier tubes at the top and bottom, and you can use the patterns to work out where in sort of this direction the interaction happened. And then you can use the time between the two signals in the liquid and the gas to tell you how deep down this interaction happened. So this will be important for reasons I will describe in a minute. But that's the kind of principle of how we look for dark matter with these sort of experiments. So now I'm actually going to tell you about the one we actually built and ran for the last sort of 3.5 years. And this is LUX, or the Large Underground Xenon Detector. And this was, as I say, a sophisticated bucket with about, I think it was 122 photomultiplier tubes viewing the liquid xenon. And we placed it underground. And as you will see from this diagram, we also put it inside a water tank. And the reasons for this are basically that not just dark matter will produce light within xenon. Any particle coming into the xenon will produce a flash of light. And because dark matter is such a weakly interacting particle, it's such a WIMP, that we know that it will interact very, very rarely. And we have to sort of, we have to remove as many other standard, boring, everyday particles as we can from coming into our xenon. So the reason we go underground is because right now on Earth, we're all being bombarded by cosmic rays from space. So these are very high energy particles that are sort of raining down on us all the time, in their millions sort of thing every second. And these particles, they make, that we don't notice them obviously, but when they come into our detector, we see them and they can look just like dark matter. So we go underground to allow the Earth to shield us from that radiation from space. And then we actually realize once we get underground that the actual rock in our sort of, this is in a cavern underground, and this rock is also radioactive. And radioactivity is just particles. So radioactive decay is particles like uranium. You might have heard of uranium and thorium elements that they use in nuclear reactors, and these just spit out particles. So we have to go even further than just underground because there's more particles that are coming from the rock that might look like dark matter. So then we use a big tank of water. And the water is actually really good at absorbing these particles, so they can't make it to the xenon. And then we actually go even further. So it's like a Russian doll, basically. And we actually only look for dark matter right in the middle of this bucket. And that's why we need those two signals from the liquid and the gas, so we can tell exactly where an interaction happened. So we can actually cut away anything that happens around the edge of the detector, because that's likely to be sort of anything that's coming from everyday boring particles coming from radioactivity in the rock or in the materials that make up the detector itself. So that's why we need those two signals and why we have to shield everything, because we really are looking for a needle in a haystack. We're looking for something very, very rare. And then I just have another little video to show you, just again to demonstrate this detection principle. So here is LUX in its water tank. And again, we're passing through this halo of dark matter. These are the dark matter particles streaming through the detector all the time. And then hopefully they might knock into some xenon atoms and create some flashes of light, which you'll see now. Here we go. So that was 3 interactions, and I wish we had that many, but we really don't. So that's the principle. So I talked about it being underground. I just wanted to show you where this actually happened. And this, like I said, it was the last sort of 3.5 years. Well, LUX actually was removed in, I think, October last year. But it was located in South Dakota in the Homestake Mine, which is now Sanford Lab, or the Sanford Underground Research Facility, or SURF. And it's actually a dedicated underground facility just for experiments that really need these very quiet, low radioactivity, low background, shielded environments. So there's some very interesting stuff going on down there. There's even some NASA astrobiology stuff going on where they can see if stuff grows in a weird place. But we're actually 4,850 feet underground. And you have to sort of, when you work on these experiments, you have to sort of get in a cage, travel down one of these shafts and go underground. It takes only a few minutes. It's very fast, actually. And it's actually a very exciting place to work. And if you ever visit Leeds, South Dakota, I strongly encourage you to go to the visitor center there, because we sell some great merchandise. And here is our signature T-shirt, which I do own one of these. I don't usually wear it outside of the house. In fact, I left it in England. But But I actually found out from one of our collaborators that we actually have a load more now. So there's all this stuff. You can buy some really exciting stuff to wear. There's even a baby grow that says dark matter on your baby's bum. So this one says dark matter matters, which I think is important. It does matter to us at least. So it's actually a really great place to work, and I also just wanted to show you some of the fun that we've actually had. So whilst, we really are working hard when we're there. We have to go underground at 7 in the morning, and we don't come up till 5 o'clock, and in the winter you don't see any daylight. But South Dakota was my first experience of America, really. So I thought I'm glad you laughed at that. So I thought I would show you some of the things that I got up to in South Dakota. So most of the time we're underground, so I have some pictures of me wearing various, protective equipment underground. And actually it's a very, very safe place to work. It really is very safe. So we have all sorts of equipment to keep us safe underground. We have training to tell us what to do in the case of a fire or if we ever need to evacuate the mine, etc. And there's a refuge chamber if we really get stuck, and we can survive for several days underground if we have to. Obviously, we've never had to, so I hope it stays that way. Also, South Dakota has a lot of interesting stuff. Mount Rushmore, the rodeo, there's Deadwood with some cowboys that are dead in that, And this war drug thing, I really don't understand this war drug thing, but, the signs are everywhere, and you can sit on a giant jackalope. So this is a really nice place to work and visit. And actually, I also put Get on TV here because the BBC from the UK, they came and filmed us, because people are actually interested in dark matter, which is really nice. And they kind of wanted to film underground. And I actually have a little video just to show my less than 15 seconds of fame. So here, I am pressing a button to fill a bucket with some liquid nitrogen, which is actually the purpose of it was to cool down some xenon, to sample the xenon, see if it was pure. But they liked the fact that there was this big red button. So here I am pressing the button. And then walking around. And then here I'm actually not doing anything. They just told me to look busy, so I'm pretending to press the thing. Oh, I don't know how that happened. So we might have to watch that again. Oh, yeah, we're going to have to watch it again, sorry. Yeah, so, but that was nice. I got to be on the TV for a few seconds. But the whole point of this was to look for dark matter, right? And actually, so as you might have realized from what I've been saying, we didn't find any with this experiment. So we ran looks for probably, I think it was about 350 days in total. We didn't see anything that looked like dark matter. So that's very disappointing, but it's not the end of the story. So, and I wanted to show you what we actually do when we don't find dark matter is actually what we can do is put limits on its properties. So we can say, so these are the plots that we tend to make. So these are kind of showing you, this is how heavy the dark matter is on the bottom axis. And then along the side is cross-section, which in particle physics speak means its probability of interacting with the xenon. And we can sort of rule out big parts of this what we call a phase space. So we can say the dark matter isn't in these parts of this plot because, we would have seen it if it was. And when we have to explain this to the public, we try to use analogies. And the one that we use for looks is unicorns, because unicorns are kind of like dark matter in that just because we haven't seen one yet doesn't mean they don't exist. So here is the plot in unicorns. So there are no unicorns in this part in the magical forest that we have searched, but actually there are still places to search. So we're not completely sure that we haven't found any unicorns yet, and we're still trying. But I just want to show you how far this analogy really goes. And when we're underground and working underground, sometimes things go wrong. And when things go wrong, actually, if things go very wrong, you're allowed to color in a unicorn and stick it on the wall. So so this is actually from our control room underground in South Dakota. And we do have, there's more than that. It's kind of embarrassing. But these are sort of some of them that you can color in if something goes very, very wrong. So we didn't find dark matter. The media likes to sort of complain about this. They like to say some things. We spent $10 million. We didn't find anything. We failed. And usually in these sort of articles online, you will find at least one person in the comments will say, "Oh, did you try looking down the back of the sofa?" And I have no response to that. But what are we going to do now we can't find it, is actually we're going to build a bigger detector. So this is the next one. This is Lux Zeppelin, or LZ. And I can't say LZ because I've got so used to hearing the Americans say LZ that I have to say LZ. And LZ is going to be about 40 times as big as Lux. So it's much, much bigger. And this is our sort of, if we ever want to make a Led Zeppelin cover album, we already have it, the imagery for it. But this is the mine, the at Surf. But basically, this is a much bigger collaboration. There's now 200 scientists, more than 30 institutions, and we're actually going global. So before, Lux was kind of just mainly universities in the US, but also a few in the UK. But now we're kind of going more global. And LZ is going to be sort of like Lux on steroids. It's going to be a much bigger, better Lux. And the whole point of going bigger is that you actually become much more sensitive to dark matter. And we actually sort of wanted to show this is kind of what it's going to look like. And it's in the same water tank as Lux, so it's going right where Lux was taken out of last year in Sanford Lab. And basically the point of showing you this was just that the green bits here are this outer detector system that this is what we're working on at UCSB. And this is kind of another detector that has its own photomultiplier tubes around the edge that's going to help to allow us to use more of the xenon within the main detector by basically, it contains something that's called gadolinium-loaded linear alkyl benzate, which I challenge you to say after drinking, but it's basically a substance that's really good at capturing neutrons. And neutrons, if they come into our main detector, they will look just like dark matter. So we're very worried about neutrons. But we, at UCSB, we're building this extra detector around the edge that's going to help capture those neutrons and tell us whether what we see in the xenon is really a real dark matter signal or not. And this is really important. Like I say, we're looking for a needle in a haystack, and we have to really know that if we see something, it's Nobel Prize winning. If we see dark matter, people will be getting prizes. And we have to know whether it really is dark matter or it was just something from the outside coming in. And that's why we're building this at UCSB. But LZ will be moving further down this plot. So this is the same as I showed you before, but actually what you see here is that this green bit at the bottom is what we call the neutrino floor. And this is kind of difficult because neutrinos are particles that we know about and we detect already, but they're very similar to WIMPs in that they interact very rarely. And we actually, they're coming from the sun, they're coming from the atmosphere, they also come from supernovae out in space, and they also come from nuclear reactors. And once we become sensitive enough, with LZ, when we run it for a certain amount of time and it becomes very sensitive, we'll start to see neutrinos. And this is kind of nice. People spend millions of dollars building neutrino detectors, but that's not really what we want, and they actually look just like WIMPs. So we will face a problem when we get down there. And here's the unicorn version of this same plot. So you can kind of see, if we get down here, it's the dark forest, and there's neutrinos masquerading as unicorns, and it is a problem. So we're really hoping that we can find dark matter in this space in between where we are now and where we will be in a few years' time with LZ. If not, we'll have to find a way around it, and it's not impossible. So I just wanted to end with some of the questions that people usually ask me about this sort of research, which is, why are we doing this? What's the point? What if it's not a WIMP? What if we don't find any? Why are we wasting all this money on this stuff? Why are we obsessed with unicorns? I think the answers, there's a lot of answers to these sort of questions. I think it's important to realize that this sort of research actually has a lot of very important spin-offs. At CERN, the guys at CERN, the particle physicists there, that's where the internet was first developed. So we got the internet from particle physicists, basically. So there's lots of things that can come from this that could be valuable to everyone. But also, as Einstein said, apparently, the pursuit of knowledge is more valuable than its possession. And as we know so little about the universe, we must be extremely rich right now. So we have to, this is important to us as physicists to just keep trying and trying to understand where we came from and why we're here. The unicorns question, the only answer I have to that is that we spend a lot of time underground, and you can go a little bit crazy when you spend all this time underground. And things like this happen. This was when we finished taking data, and we had a little party, and there was a unicorn piñata. But anyway, thank you very much for listening to me.
Thank you very much, Sally. And we should say that if you want to have a closer look at this photomultiplier detector, it'll be in the front desk. So you can go have a look at it there. And we're going to take now a short 5-minute break so you can stretch your legs, get some drinks. And in the meantime, text your questions to 805-55-AOTSB. We've already received some excellent questions. Keep them coming. The number is over here on the board. It'll be on the screen. 5-minute break. Okay, we'd like to get started again. Thank you for all the excellent questions. There are many more questions than we can answer, so I apologize in advance if we don't choose your question. But if we don't, you might have noticed some of us are wearing glowing star pins. Please feel free during the next break or staying after the event. If you have more questions that we did not answer, just ask someone with a glowing star pin and they will either know the answer or know who to point for the answer, or we may not know the answer at all. So, but it's worth a try. Okay, so we're going to get started with questions here. And I remind you, if we select your question, please see Sandy in the front desk to get a free postcard. Okay, here we go. First question. Is antimatter and dark matter the same thing?
So no is the answer to that. Antimatter is basically sort of like matter's sort of evil twin. So all the particles that we know about have an antimatter partner, and this is like a symmetry, like a law of nature. So every electron has an anti-electron, which is called a positron, which is basically exactly the same mass, but it has the opposite charge. So this is kind of the key thing about antimatter, is it has the opposite charge. So an electron is negatively charged, a positron is positively charged. And then all the other particles that we observe, they all have their own antimatter particle, and then when you bring them together, they actually just annihilate and produce energy. So, and actually one of the biggest mysteries in physics today is why are we all made of matter and not antimatter, and why is there anything, to be honest? Because in the early universe, everything should have been made in equal amounts, but it clearly wasn't, because more matter was made than antimatter, because we all exist and we're all just made of matter, and we haven't turned into energy. But dark matter is just another particle that's made of normal matter, but it will have its own antimatter particle too. And that's what we do with the indirect detection method, is look for the dark matter annihilating with its own antiparticle. So dark matter has its own anti-dark matter as well. But they are two very separate things.
Okay, so you mentioned the WIMPs. Someone in the audience seems to know that there was another candidate for dark matter called macho. What is a macho, and does anyone still think that could be dark matter?
So a macho stands for a massive compact halo object, and these are basically just things that we understand, sort of very dark stars, like brown dwarfs that are very old stars that don't give out light anymore, or black holes. And people sort of thought maybe dark matter is just some of these objects that aren't giving out light anymore, but they are still the sort of stuff that we understand. But they actually, there aren't enough of them, basically. So when we sort of add up the mass, so we can use all these amazing astrophysical observations, like the cosmic microwave background, to add up how much matter there is in the universe, and it doesn't add up to be enough to make up dark matter. So we know that dark matter can't just be these big heavy objects like the machos, because there just isn't enough matter to explain what we observe. But and also sort of the thing that we see within galaxy formation. So when we see galaxies forming, and we can sort of look at the structure of galaxies and how they've managed to form, and we can't actually explain that without some sort of dark matter that isn't normal everyday stuff like old stars or black holes. And it means that you can't actually produce galaxies in the number that we observe in the universe today without something heavy and non-interacting like this weird WIMP dark matter. So we know for sure that it isn't machos at all.
So you mentioned once the detector gets sensitive enough, you're going to start seeing neutrinos. So how do you tell a neutrino from a WIMP?
So we have some ideas. Like, this is going to be a problem if we get down to the point where we start detecting neutrinos and we still haven't found dark matter. But the main source of neutrinos is actually the sun. So the nuclear fusion processes in the sun produce neutrinos, and that's where most of the neutrinos that arrive at Earth are from. And we can kind of rule those out just by, if we can build a detector that can tell you what direction the particle has come from. And there are some ideas for these sort of detectors. So there actually are even some directional dark matter detectors going on right now. Generally, they're gas ones, and they sort of, you can see tracks of particles through them. So you can tell you where the particles come from. If you can see it's come from the sun, you know it's a neutrino, basically. So there are these ideas that we can tell that you know which particles are neutrinos and which ones aren't. So that's kind of, hopefully we won't have to get that far. But
another question, I think related to the ones you posed on yourself on your slides, is if we find dark matter, what's the use? Now, is it okay if I take this one, or do you want?
No, go ahead.
Okay, so that's a great question. Say we detect dark matter, what's the use? Okay, so I'm going to tell you a story about a guy named J.J. Thomson who discovered the electron. And when he discovered the electron, he went to a bar, raised a glass to the least useful discovery in the history of science. Okay? That's how he celebrated discovering the electron. Can you imagine life today without anything related to the electron? Okay, everything we do today runs on electricity, and we would not have that without the electron. So, the moral of this story is, we have no idea what it's going to be good for, but discovering a new particle might be the next revolution in technology. So we just don't know, but it's pretty much guaranteed to be a huge thing. Okay, so I think that's, you know, and that's a good question for anything that's kind of curiosity-driven in science. We don't know what it's going to lead to, but it always ends up leading to amazing things. Okay, there's another question I liked, which was, what will it take to convince you that dark matter does not exist?
That's a tough one to answer. There are actually theories. I mean, when I was writing my thesis last year, there was a theory that almost explains every observation of dark matter using stuff that isn't dark matter. But I don't know. It would have to be something really big. I can't really tell you what it would be. I don't know. That one's had me stumped. I think it would have to be something. Everything points to it being being a particle and being a WIMP, and it seems like it would have to be something really amazing, like some brand new theory that really explained every observation that we have. You know, that right now we use dark matter to explain, to convince me. But or some real.
Okay, last question. Please settle a discussion. Where in the UK are you from?
Yeah, I'm from Nottingham, so you know Robin Hood. That's where I'm from. I don't have a very strong Nottingham accent. I can tell you that my family all. Oh, I didn't even. It's broken. They call me Saleh. Is how where I'm from.
Okay, thank you very much.
That was great. Sally's advisor is here. He called her Lorentz invariant solid gold, and I would agree. That's a physics joke. Physicists will get it, though. All right.
Okay, we're ready to move on to astronomy in the news. We have had a lot of astronomy in the news this month. So we only picked a few stories. We couldn't do all of them, but here's what we thought was the most interesting this month. And we start with Jupiter. So the Juno mission, which we've been following since it arrived at Jupiter 1 year ago, has been orbiting Jupiter closer than any other mission before. Every 53 days, it passes really close to Jupiter. So it's done that about 6 times since it arrived. And now, finally, they have released the first science results from this mission together with some incredible pictures. Okay, so we show you a lot of things at Astronomy on Tap, and we don't use the term mind-blowing very often, but I think it does work for these pictures. So they released the first science results now in 46 publications. That's how much stuff they had learned new about Jupiter. The main things are, we knew Jupiter as the most massive planet in the solar system, has the strongest magnetic field, and this is one of the challenges of sending a spacecraft so close to it, and it turns out the magnetic field is twice as strong as we thought. is one thing that they discovered. They also found these cyclones in the south pole of Jupiter. This is a picture of Jupiter from the south pole. These circles there are cyclones that are 600 miles across. We don't know how they are formed. We don't know why the South Pole is different than the North Pole in Jupiter, and so that, raised more questions about Jupiter. And another thing they found, there's this question, the outer layers of Jupiter are all gas. Question, is there a core inside? And it's, people saying, is there a core, a rocky core inside, or is it all gas all the way down? And it turns out it's kind of a little bit of both. There is a core, but it's not directly, a solid core that ends where the gas start. It's like a core that kind of fizzles out into liquid metallic hydrogen near the core. I had to look that up to see what it is. So these are just some of the exciting results coming out, and some more images of Jupiter here like we've never seen it before. So you can see these like ice, snow crystals there. We don't really know snow of what material, but it kind of looks like snow there in the atmosphere of Jupiter. Here's another storm in Jupiter. And one of the nice things is that NASA is making all of the raw data coming from the satellite public, so anyone can download this data and process the images and try to get out more details. So these are actually now images made by amateur astronomers who are getting the data from this mission and making these beautiful, beautiful images of Jupiter. And one of them even went further out and took 2,700 images and compiled them into a movie showing the orbit of Juno, of the Juno spacecraft as it flew through past Jupiter in one of its orbits. And so you'll see like these lighting changes are artifacts from the camera, from joining all of these images together. You'll see at some point like some dark spots, those are artifacts as well. But this is real images from the flyby, one of the 6 flybys that it did of Jupiter. So yeah, this is just incredible. Yeah, because those black dots are not real, but everything else is. So you can see the structure in the clouds, the storms going on. And then it's going to swing over to the South Pole, which is the images you saw before.
And some of those little white dots are like clouds with something like snow coming down onto the atmosphere. So of course, it's just gas all the way down.
So Juno is still there in Jupiter, and it's going to orbit a few more times. And the next close approach it's going to make to the most recognized feature of Jupiter, which is the Great Red Spot. So the next close approach, which is going to happen next month on July 11th, is going to be of the Great Red Spot, and we can't wait to see what images are going to come out of there. Okay, so it's all available online if you want to watch it later. It's just spectacular.
All right, next up, Tabby star. For those of you who have been following astronomy in the news, we've talked about it before, and in fact, the person who discovered this, Tabitha Boyajian, in fact, we had LCO brought her to town, and she gave a talk about this. This is a star that has dipped in brightness. Here are some plots as seen from the Kepler Observatory, a space-based observatory. And this star dipped in really weird ways. Normally, you get a dip every so often if a planet passes in front of a star, but that's periodic, right? It might happen once a year or something like that. But these had really weird dips that weren't the same every time, and they didn't obey an obvious period. And in a planet, you just it goes down and comes back up. But these do all this weird shape. And so people have speculated that this is something crazy and different. One of the things people speculated about is the alien megastructure, okay? So people said, this is the alien. Now people are like, oh, now I know what star you're talking about. Yeah, the alien star, yeah. All right, it's, maybe some aliens built some kind of crazy. But you gotta design a really weird thing around this star, okay, for if aliens did it. Okay, I will tell you at the end of this talk whether or not aliens did it, so pay attention, okay? So, all right, that's the idea. Okay, in Wired, they even wrote this article about, okay, aliens in orbit, probably not, but a 100K on a Kickstarter to check, okay, sure. And that Kickstarter was to buy time on our observatory, Las Cumbres Observatory. Okay, so here's a quote from the article. $100,000 would allow her team to monitor the star for a year using our telescopes. And it's a long shot, but she doesn't have the regular resources to do this, but they're going to try it. And so that long shot paid off. They got the Kickstarter funded. They bought time on the observatory. We've been monitoring the star for quite a while. And I will remember the Kepler spacecraft can no longer make these kinds of observations in the way that it could before. And so our observatory has a bunch of telescopes all over the world. And as the Earth rotates, we can always keep observing something 24 hours a day. That's the unique thing. And so here's what happened. They found that the star was dipping based on another observatory's observations plus our observatory's observations, and sent out stuff on Twitter saying, observe this star, all astronomers. So all the observers that were like sometimes we get alerts on Twitter and say like, oh, we better start observing stuff. We were already observing with our observatory. And in fact, this became such a big deal that even when Apple was showing off its new stuff last week, when they showed off the new iPad and so on, the screen they had on there was this news story saying astronomers are scrambling to observe this star dipping. Okay? So here's the data. This Fairborn is another observatory, and then LCO are two of our sites at Maui and the Canary Islands. And you can see that the star was at 1, that's its normal level, and then it was dipping over the last few days here, and then it started coming back up. And from the scale over here, you can see it's been dipping by about 2%. So this is one of the smaller dips. Some of the other dips that it's had have been as much as 20% of the light of the star has been, wiped out by some process that we don't quite understand yet. So how do you do this? Why is it that some of these dips are 2%, some are 20%? This is the first time we've been able to see it in real time and make observations across many wavelengths and figure it out. The Kepler stuff was done after the fact. To tell you one theory about how this could happen, we have a video here by Brian Metzger and Nick Stone, two astrophysicists at, where are they at? Princeton. And
Columbia.
Columbia?
Yes.
Okay. Well, one of those New York places. They are, Brian, I know Brian very well. He's a good guy. Anyway, they're explaining their own theory here in this video in a very long 15-minute video, but we're only going to show you a little tiny highlight, but you can go online and see the rest of it.
And just before the video, I want to mention, I remember that because this dip was discovered at our observatory, they told us we get to name it, right? So we get to name the dip, okay? So clearly, it's going to be called Dippy McDipface. Okay. No, it's
they
not.
didn't go
Actually,
for that. They didn't go for that.
That was not accepted. Unfortunately, that suggestion was not accepted. Okay.
So the name that was picked was LC for Las Cumbres Observatory, but whatever.
Yeah, fine.
Yeah, not as good as...
Here's the theory.
Sound?
We imagine an exoplanetary analog to these gas giants being excited to orbits of higher and higher ellipticity and smaller points of closest approach to Tabby's star, then these moons will suffer a very interesting fate. Before their planet impacts Tabby's star directly, the moons will be detached by the gravity of Tabby's star from their orbits around their planetary host, and will be placed instead onto very elliptical orbits around Tabby's star itself. If these moons are analogous to the satellites of Jupiter and Saturn in our own solar system, their cores are made of rock, but their outer layers are made of much more delicate elements like water and ammonia ice, which exist as solids only at very low temperatures. However, once these moons are detached from their host planet, their elliptical orbits will carry them very close to Tabby's star, with points of closest approach even closer than Mercury's orbit around our own sun. The scorching temperatures experienced by these detached exomoons at their points of closest approach to Tabby's star will lead to violent and massive evaporation of the water and other forms of ice on their surfaces, creating expanding layers of gas and dust evaporating from the exomoons and generating large-scale clouds of gaseous and dusty debris, which could explain the transits that the Kepler satellite observed.
All right, so if you didn't get that, it's like if you have gas giant planets like Jupiter with a bunch of moons around it, and it gets really close to the star as these orbits can actually change over time and get more elliptical, you can rip off those moons, the planet goes crashing into the star and actually gets disrupted, produces a lot of gas, but then these moons evaporate and produce these crazy clouds that can block out a light of the star. Okay, so it's an interesting, we don't know that that's what's going on, but it's an interesting case where we get observations, they come up with a theory, we have new observations, and now we can test this. So here's some of the new data, and up at the top you can see that they've overlaid one of the previous dips on this dip, but multiplied by a certain factor. And so actually what seems to have happened is that there was a dip, and then there was another dip about 260 days later, and then there was a third dip that we didn't see because nobody was observing it. But then now they've observed the fourth time this has happened, and as predicted, it happened sort of on schedule. So that says there is some periodic nature to some of this, so that implies that orbits are involved. And also, dust is probably involved. So this is Tabby's Twitter feed, and she says that based on the new data from our observatory, the way that the light changes with wavelength indicates that there is some dust probably involved. So though that could actually be a part of those guys' theory, so that's one of the theories that's still alive. Sadly, that means that alien megastructures are not what is happening. So sorry. But continue to support the Kickstarter because it helps our observatory to take these awesome observations. All right.
Okay. So Sally mentioned the experiment she works on. There are other dark matter experiments, and one of them was in the news. So this one's an experiment that was not very creatively called Xenon. It's the same principle similar principle that Sally was talking about, and then they upgraded to an experiment called Xenon 1T or 1 ton, because they're using now 1 ton of xenon, and they started running a month ago, and they have not yet seen any dark matter particles. So here's the limits you saw from Sally before. You see the LUX experiment, okay, that she was describing. That's like above this line is where the unicorns are not, and below it is where they could still be living, and the purpose is to try to get this line as low as possible to corner the unicorns into one corner and then find them. So you see the Xenon 1 ton experiment from this week is just slightly is slightly more sensitive than the LUX experiment, but Sally did ask that we point out that at the top left of that plot, it's a little hard to see, the LUX experiment is still a little bit more sensitive. Okay, and the new LZ experiment is going to be more xenon than this one, so they're going to be more sensitive than this competing experiment.
All right, all you upstairs people, shut the hell up. It's always the upstairs people, all right? People are trying to listen, so be quiet, okay? All right, so the next news item here is a search for failed supernovae, a search for direct collapse to a black hole. The idea is to monitor a whole bunch of stars and see if one just disappears. So this was an idea that came out in 2008, and people have been working on it ever since to try to see if this is a real thing. So the original authors called it there's a title here called A Survey About Thing. Okay, so the cast of Seinfeld had to look at the paper, obviously, and say, I can see Elaine there, looks a little skeptical, like I don't know if they got the quantum efficiencies right. But they've been working on it ever since, and just now, almost a decade later, they have a paper saying that there is a search, they found the disappearing star with the Large Binocular Telescope. Okay, So scientists have built this giant telescope in Arizona. You can see at the bottom the size of like a door or a window or something like that. You can see how big this huge pair of binoculars is that they mainly they use to look at football games really far away, okay? But occasionally they look at stars, and they have found one that disappeared. Okay, here it was. Actually, this is a Hubble Space Telescope image from 2007, and here's a new image from 2015, and there is nothing there. And so when I was showing this to Yair, he said, how do you know that David Copperfield didn't do that? Because he made the Statue of Liberty disappear. Maybe he's really upped his game. Okay, so what you have to do, actually this star was a 25 solar mass red supergiant, seems to have gone away. All right, that's a big deal. What you have to do is monitor it over the course of the whole, however many years it was gone. And so this is actually monitoring the light over time. This thing on the bottom is days. Okay, so you can see 54,000 days, 55,000 days, 56,000 days, and so on. So this is long periods of time. And on the left is basically brightness. What you can see is all these different color curves. It got a little brighter, and then it fell way down to almost zero. The black curves there are in the infrared. So there's still some signal in the infrared, but in the optical, the thing disappeared. So their claim is it was something like a failed supernova, didn't produce a ton of energy like a supernova, but it then disappeared straight to a black hole. So a star going straight to a black hole. We study supernovae. We're a little skeptical because there's still some infrared light. They have some explanations for that, but it remains to be seen. If so, this is a big, big deal. It could be that if this is held up by future evidence, it could be that 20 or 30% of black holes get created in this way.
Okay, so going back to our own star, the sun, NASA announced that a new mission to study the sun. It's going to get closer than ever. So it's going to be launched next year. And it's going to orbit the sun 24 times, getting really, really close to the sun. So close, in fact, that some news articles said it's going to touch the sun. So no, it's not going to touch the sun. But it's going to get to within 4 million miles of the sun, which is 7 times closer than we've ever got before. And it's pretty hot that close to the sun. So this spaceship is going to have to withstand temperatures of 2,500 degrees Fahrenheit when it gets close to the sun, so that's why it has this weird shape with a heat shield on the front. Also, I should say that's not a real picture of the spaceship near the sun, A, because it hasn't been launched yet, and B, when it does, they're not going to send a camera to take a picture of it. So, that's a computer animation of what it would look like in a year. And so part of the purpose of this is to study 2 very mysterious things that we don't understand about the sun. One of them is the solar wind. The sun is just emitting particles all the time, and some of these get accelerated, and sometimes they can be dangerous for satellites or astronauts, or even here on Earth, they can cause power outages. So we want to try and understand the solar wind better, and we can do that by getting really close to the sun and trying to figure out what's going on. And the other thing is that the surface of the sun is a few thousand degrees, but the upper atmosphere around the sun is a few million degrees, and that's the other way around of what it's supposed to be. The atmosphere is supposed to be cooler than the surface, and it's the other way around in the sun, and we don't know why. So this is going to try and study that. So when it gets really close to the sun, it's going to be moving pretty fast at about 450,000 miles per hour, which is LA to Santa Barbara in 1 second. Okay, so that's pretty fast. And so it's going to be one of the fastest spaceships, and it just got a new name. It's going to be named after Eugene Parker, who's this guy over here, who 60 years ago developed the theory of the solar wind and celebrated his 90th birthday this weekend. So this is actually the first time that NASA is naming a spacecraft for a living researcher, and he's the first one that gets his name on a spacecraft. So he was pretty happy about that.
And in gravitational wave news, people who have been following Astronomy on Tap know that since the first one, we've been talking about gravitational waves. They were first detected more than a year ago, and now the most recent detection was just announced. It's the 3rd time gravitational waves have been announced, and two black holes are the culprits merging together. So if you look on the left, you'll see these little wiggles, and those are signals from these massive detectors. There's one in Louisiana and one in Washington State, and they actually detect distortions in space-time caused by the ripples by these black holes merging together. So the most recent one is on the bottom. Now there are 4 here, but that's because the green one wasn't really significant enough to call it a real detection. But this new latest one in purple is. On the bottom, you can see how long it took. And so this little wiggles in space-time followed by the black holes merging together took less than a second. And then on the right, you can see the area on the sky that must have come from. We then use our telescopes at Las Cumbres Observatory to see if there was an explosion associated with that. And we haven't seen one yet. But the people that do LIGO have been able to measure the mass of the black holes involved. And before LIGO, this was all of the black hole masses that we knew about in terms of stellar mass sort of size black holes, and only up to about 10 times the mass of the sun. But when LIGO turned on, they found that there are these 30 solar mass black holes that merged together and produced something like 60 solar mass black hole, which nobody really saw coming, and it really challenges a lot of our theories. They also saw another one that only got up to about 20 solar masses combined. This one's in the middle. It's 2 black holes, about 20 and 30 solar masses that add up to something about 50. If you look at the numbers up there, you see there's 2 solar masses missing, and all that energy got radiated into space. So it's something like 2 times the mass of the sun that got turned into energy that's what we picked up in this experiment. The new thing about these is that they're about 3 billion light years away, so it's a little farther than we've been able to see before. It's about twice as far as the previous detections. And then also, their spins are not aligned. Here's an artist's conception of 2 of these black holes coming together, and they're not spinning the same way. If they were formed in the same system, like if this were 2 binary stars, really massive stars that made black holes, we'd expect them to be forming in the same direction, spinning in the same direction, and then merge together. But that does not seem to be what was the case, and so one of the people describing the experiment said, instead of them coming together as a waltz, it was more like a breakdance, okay? That was a little chaotic.
Okay, next up, the Gruber Cosmology Prize was announced last month, and it was given to a professor at UC Santa Cruz called Sandy Faber. Just to illustrate how big of a deal this prize is, last year it was given to the entire LIGO team for their detection of gravitational waves. This year it's given to this one person, Sandy Faber. So she did some really revolutionary research in astronomy, including figure out a new method to measure distances to galaxies. She also co-wrote the first paper that reviewed everything we knew about dark matter at the time, and that is really considered the turning point of when astronomers and physicists started really taking dark matter seriously as a thing we need to investigate following her paper. She was also involved in developing instruments for the Keck telescope in Hawaii, which is the largest telescope, most sensitive telescope on Earth, and in building instruments for the Hubble Space Telescope, which is, again, our best telescope in space. So she's probably the only person who was involved in both of these great observatories. She also discovered with her group that there's probably a supermassive black hole in the center of every galaxy, and that the mass of the black hole scales with the mass of the galaxy, which is an unanswered question to this day when we're trying to understand these very massive black holes. So very deserving prize, and we're very happy for she's one of us in UC. And I want to give you a quote from her, which she says, "Astronomical knowledge is probably the most important single discipline that you need to know in order to be an informed citizen of Earth. It tells us how we got here, and furthermore, having understood that, we can extrapolate more confidently for the future." So we really hope we can get Sandy Faber down to Santa Barbara to give a talk and tell us about her research. And here she is getting the medal, a National Medal of Science from President Obama, and now the Gruber Prize. So congratulations to Sandy Faber.
All right, last story tonight is about a cold spot in the cosmic microwave background. So you might have seen this picture in Sally's talk. It is the afterglow of the Big Bang. And so this is a projection on the sky of temperature differences in microwave energy. And these red spots are hotter and the blue spots are colder. Now, the temperature difference here is like 0.000015 degrees Celsius colder in the cold spot. Okay, so it's not a lot colder, but it was a big deal. If we can see the next one. Okay, so this all comes from a paper called Evidence Against a Supervoid Causing the CMB Cold Spot. So why is it a big deal that there's a cold spot? Well, the odds are only about 1 in 50 that this would happen by chance, and one of the ideas is people said if there's a void along the line of sight, in other words, places where there are not a lot of galaxies, that could make an apparent cold spot on the sky that's not real. What these people said in this paper is that no, that's real, okay? So if you look at the quotes in the paper, they say, well, it's possible that it could be because of a remnant collision between the universe and another bubble universe during the early inflationary phase, but it must be borne in mind that without a supervoid, the cold spot may still be caused by unlikely statistical fluctuation, blah, blah, blah. Okay, that seems like a bunch of boring astronomer talk, but of course, the media took this and ran with it, and holy crap, another possible universe. Scientific American had a relatively reasonable headline. Could cold spot be a bruise from a collision with a parallel universe? Okay, but then other people get a little worse as you go down the spectrum here. Is another universe sitting too close to us on the multiverse bus? Okay, and then mysterious cold spot in space could be proof of parallel universe, scientists say. Notice the picture is of the Crab Nebula, which has X-rays in the center, one of the hottest spots in the universe, not one of the coldest. And then as you go down in class, you get to scientists think they found proof of a parallel universe, okay? Now, we've already gotten to proof of a parallel universe, and in these articles, people start to talk about, well, there could be another version of you out there. Even if it were another kind of universe, nobody said it was an alternate version of our universe or something like that, okay? And even getting down to Mashable, we live in a parallel universe. Wow. Wait, what? And that, in the article, they actually had good science, but of course they wanted the clickbait headline that says, oh, we live in a parallel universe, okay? So that is a total disingenuous lie. But my favorite is this article from something that says, beam me up, scientists discover possible evidence that we live in a parallel universe, which has this great graphic. So you know this is a legitimate publication here. And it also has this quote. It might sound like the kind of thing you think about after you've taken a bong hit, but apparently in one universe you might be a prime minister, while in another you could be made of Nutella and at this very moment be facing the prospect of being spread onto a pancake. I couldn't have said it myself any better. That is just science right there. Okay.
And that concludes Astronomy in the News for today. We're going to take another short 5-minute break, and we'll be back with the Eric and Brian talking about what it takes to run a worldwide observatory. So stick around.
So it is my pleasure to introduce two people tonight who I have known for a really long time. I got here in 2008 to Las Cumbres Observatory, and these guys were already working here. This is Brian Haworth and Eric Saunders. They're going to tell you a little bit about how the whole observatory works. I will start off talking about Brian, and Brian is head of the IT department, and so when all the computers and telescopes and things break, it's Brian that we go to try to get them fixed. And he has this vicious dog in his office who, when you go in, it serves two purposes. One, to be cute and you can pet it. His name is Darcy. But also, when you go in there and you have a problem like me and you can't get your computer to work, the dog will just bark you out of the office and you have to leave and figure it out yourself, okay? But Brian obviously really loves animals, but he also is like an IT guy that has to deal with nasty. Wait a second. He has to deal with nasty hardware that doesn't always work. And so I'm going to relate both of our speakers tonight to characters in Office Space. So I will say that Brian is this guy. All right. Now, you think I'm just making a joke, but here he is actually throwing away one of our servers in the dumpster and was super excited about it. Okay. Because he does have to support massive numbers of computers, hundreds of computers that not just run the people that work at the observatory, but also that run all of our telescopes, and the actual telescopes themselves break. Astronomers complain if this doesn't work, and it's incredibly hard to support all this stuff across many different operating systems, and he's mostly done it with a staff of 2 people, him and one other person, this whole time. So it's quite incredible. He is basically a wizard, but that brings us to this other picture I dug up of him in school when he was a little kid. This is him in front here, which is either something, it reminds me of some crazy combination of Stranger Things, Harry Potter, and the Beatles all mixed together, okay? He grew up in the UK, I should say. There's a whole British invasion thing going on tonight, as did Eric. Okay, we tried to build a wall to keep them out, but we don't have the funding for that yet. But as I mentioned, Eric is the other person also giving a talk tonight. He started off as a programmer at LCO. He then rose up the ranks and he built the scheduler that schedules all of our telescopes. So how do we know what observation goes where? This piece of software that he wrote sorts it all out and figures out how to get all of the best observations, which is an astounding piece of code that nobody else has at any other observatory in the world. So then he became head of programming, and then he got promoted even again, and now is head of engineering at LCO. So in the office space world, he started off as the guy in the cubicle, but now he's the other guy. Okay. So,
we have sort of a problem here. Yeah, you apparently didn't put one of the new cover sheets on your TPS reports.
all right, so he's now a manager, but actually he's done a really good job of managing a lot of the output of the observatory. Although here he is at Halloween at the observatory. Now, you might think that's a costume, but actually that's how he really looks. He puts on makeup to look normal. Actually, he is on another day, and I heard he got in on the bus and was standing next to an old lady. It kind of made her a little uncomfortable, thinking about her remaining years on this earth. But if you notice a death-related theme here, he was also in a death metal band when he was younger. And now you say, why is this weird psychedelic-looking kind of thing associated with death metal? Well, there's a subgenre of death metal called stoner doom that they were involved in. And if you think we don't have a clip of that, you don't know us very well. Okay, so let's hear what his band sounds like. There's only one CD of this, and we tracked it down. All right, so that guy is in charge of most of Las Cumbres Observatory. And so here we go, the Bert and Ernie of Las Cumbres Observatory, Brian Haworth and Eric Saunders.
How do we follow that? Well, I never know where they dig this stuff up from. So tonight, we're going to give you a quick overview of Las Cumbres Observatory and what it takes to run a global telescope network. But before we begin, I know you've had some sort of introduction to Eric, but I wasn't.
Some sort of introduction.
Some sort. I wasn't privy to it, being told to be hidden out the back. So Eric Saunders, Director of Engineering for LCO. He's been with us for 10 years now, and he was primarily concerned with writing the software that actually keeps the observatory observing. But as you might have been told earlier, he's also an astronomer by training. He likes to keep quiet about that, though.
And Brian is our IT manager, and he's actually been at LCO even longer than me, 12 years. And his favorite thing to do is to turn things off and back on again.
So a long time ago in a galaxy far, far away, an engineer had a dream. His name was Luke Skywatcher. No, that's not right. His name was Wayne Rosing, and he was studying to be a Jedi Knight under an equally short of stature guy in a scruffy... Wait, no, that's a lie too. He was at Apple Computer at the time, and that's when he had his Newton moment, and thus it all began. He dreamt. He coded. And yes, he danced.
So you may know Wayne from such successful projects as the Apple Lisa.
Which he ran.
The Java programming language.
Which he ran.
The omni-page optical character recognition thing that I never heard of until 5 minutes ago.
That was at a company called Sierra, and Wayne was the chief technical officer of that company as well.
And Google.
And Google, of course. Now, at Google, at one point, all projects reported directly to Wayne, including Gmail and ads. So, yeah, this is a guy who likes to think big.
Now, not only was he working on all of those things, but in Wayne's copious free time, he was also a keen amateur astronomer. And he had an idea, something he'd been thinking of for a little while, a vision for a unique observatory. What would happen if you took some state-of-the-art telescopes, you made them robotic, and you allowed them to be movable from far away?
And scattered them liberally all over the globe.
And then connect them over the internet?
And then coordinated the whole thing like some great big global scientific instrument using computer science. So, that's one thing you need to know about Wayne Rosing. He was obsessing about this stuff back in 1982. Now, in 1982, whilst the internet was around, the World Wide Web wouldn't be a thing for another 9 years. Ronald Reagan was in power. We had absolutely fantastic TV. Even in the UK, this stuff came over. And yes, unfortunately, we had Margaret Thatcher, who was busy scurrying the pants off the Argentinians. Now, back in 1982, Eric was busy learning how to walk.
And Brian was doing something with a very big book about water.
And back then, Wayne's dream seemed more like sci-fi than reality. So that's the first thing you need to know about Las Cumbres Observatory that makes us very different to many other observatories out there. We are not traditional. Now, you may remember that by training, Eric was an astronomer. So Eric, could you tell us what it used to be like when you wanted to go out and observe with telescopes?
I sure can, Brian. Well, a long time ago when I was a PhD student, I went on an observing run to La Palma. And out there for 2.5 weeks. And I got to the mountain, went up the mountain, and then I lived this vampiric life for 17 days. I would wake up, the sun was setting, I would have dinner for breakfast, I would see nobody, then I would go to the telescope, I would hope the telescope worked, I would hope that there was enough coffee because I was going to stay up all night, I was going to hope it was clear, because if there were any clouds, it was all over. And then I would observe, and I would just observe and observe and observe. And at the end of the night, I would come out, the sun is starting to rise, and I'd go to bed. And then I'd wake up again and do it again. And it was exactly the same every day, except sometimes it was cloudy. It was like this weird Groundhog Day thing. It just went on and on and on. And at the end of that, I got all my data, and I put it on magnetic tapes, because that's what we had at the time. I took this big rucksack of magnetic tapes back to the UK with me. And when I loaded the data and tried to look at it, half of it didn't work. Half of my tapes were corrupt, so I had half the data. That's a traditional observing run.
Well, that's typical, but that's not what we do, because we are entirely robotic. You don't need to go to exotic places and far-flung mountaintops like out here in Tibet to do your observing. And that's because we have Eric's fancy software to deal with it.
What is that? So, yeah, I'm really sorry, astronomers. You don't have any reason to go anywhere anymore. From the bottom of my heart, at LCO, you don't have to do anything. You just have to use a web page. Sorry. So you don't have to be cool and clever and have a telescope that you look through anymore. Instead, we have very clever machines and computers that we use to help you do your stuff. Now, I want to be quite clear. This is not remote control. It's not like you press buttons and move telescopes around. Instead, what you do is you ask us for things. So you and lots of other people ask for stuff, right? You say, I want things to happen on your network. And we decide, or the LCO scheduler decides, what it's going to do and when it's going to do it. So how does this all work? I mean, what is LCO really? It's these people. This is a recent photograph of the LCO staff. There are actually about 40 staff at LCO. It's not very big. There's about 30 of them on this picture.
No, there's more than 30. Look, there's the dogs.
Okay, there's the
We
dogs.
like the dogs.
There's the dogs. And we have a few more people who are spread around the world to keep the ships operating from far away. And we have people who are always in transit.
Yeah, such as Yair and Andy. They're always flying off somewhere.
But there really aren't very many of us.
So, what does it take if you want to have an observatory? What do you need?
Well, the first thing you're going to need, Brian, is a telescope. And you're going to need somewhere to put it, because you want to keep it nice and dry.
And you're going to need some way of pointing it so that you can look at things. And then you're going to need somewhere to put it. Now, we like our sites to be remote so that they're dark, and we also like them to be high so that you don't have to deal with atmospheric effects such as clouds and things like that. So, here we have a snippet from BBC TV's Stargazing Live, and this is our observatory out in Australia, which featured our very own Mark Willis. It was later shown on ABC, which is the Australian broadcasting companies. It's pretty cool. Now, if you want to have a worldwide observatory like we do, you're going to need to replicate it all over the world.
Yeah, so right now we have telescopes all over the world, 18 telescopes distributed, and that's how we do our stuff.
So, what do we have? Well, to begin with, let me explain how we refer to telescopes, the optical telescopes. We refer to them by their primary mirror size. Now, the reason that we do this is that the primary mirror is the thing that collects all the photons, it gets all the light, and that is the stuff that makes the science happen. Now, at LCO, we have 3 classes of telescope.
So our baby telescope is 40 centimeters, and that's about the size of a washer-dryer combo.
Yeah, or R2D2.
Then we have a bigger one. This is our 1-meter telescope. If you put it on its piers, that's about 15 feet high, which is about the size of an average giraffe.
A little bit bigger than C3PO.
And then our monster telescopes are, and the 2 meters are what you just saw in the video. And these are big. They're as big as the nose on Washington in Mount Rushmore.
And at this scale, unfortunately, C3PO is nothing more than a golden presidential bogey.
So one of those 2 meters is incredibly heavy. It's about 30 tons. It's made of thousands and thousands of parts. This is the underside of the 2 meter wired up. So you can see it's not a simple piece of equipment. And you've got to be careful with stuff like this.
Yeah, you sure do. These things are really big. As he said, they're about 30 tons. They can crush you like an ant. So what you really need is something like an AZ safety certification. So here we have a 3D rendering of one of our 2 meter systems. We have 2 of them, one in Australia and one in Hawaii that unfortunately sometimes I have to go to, so life sucks. So here you can see the telescope. It moves absolutely silently. It really is a work of art. It's a thing to behold, and it generally doesn't go wrong. So, but that's not all. That's not all. To make all this happen, you're gonna need computers, because without computers, you can't do the magic.
So, Brian, what computers do you have?
Well, we've got a hell of a lot. We actively monitor 634 servers across our network, and that encompasses 10,000 unique services. But wait, that's not all. Each telescope requires about 40 different services and systems to be able to run. So sites like our site out at Chile has something in the region of 250 systems on the mountaintop alone. But wait, that's not all. We have servers back in our Galita office and now out in the cloud. And these servers, they store the data that we get, they process it, they offer it back out to the astronomers and the public like yourselves who want to use all this. And that's how we deal with our days worth of data.
Day or night, Brian?
Yeah, day or night, of course. So, let's put this into some sort of context. When Wayne started his crazy idea, we were using 3.5-inch floppy disks, which, as you can see, are coincidentally 3.5 millimeters thick. Now, I can get away with using both imperial and metric measurements because I'm British, and as you know right now, we have no idea where we fit within the European Union. So, who out there remembers how much data you can hold on a 3.5-inch floppy disk? Anyone? 1.44 megabytes. Now, each day...
That's an impressive piece of useless knowledge that somebody had
You
out
need
there.
to know that.
Very good.
Thanks, Kim. Yeah, so each day, we bring back 70 gigabytes worth of data. That's every single day.
How many floppy disks would that be, Brian?
Well, glad you asked. So, if you were to pile those floppy disks on top of each other, enough to store 70 gigabytes worth of data, it would reach a staggering 572 feet high. Now, that's nearly as high as the Space Needle in Seattle. Or, to put it another way, it's almost as high as the population of Isla Vista during Halloween. So, this year alone, we estimate we will bring back somewhere in the region of 25 terabytes worth of data. So let's put that into context. 25 terabytes worth of data. That's equivalent to 2.5 Libraries of Congress. And I've still no idea what Libraries of Congress are. But I was told that's what you guys like to see. Another way to look at it, it's 1.5 years of back-to-back movies. Some starring our very own Wayne Rosing. Or, to put it another way, it's 48.5 years worth of constant streaming music from the likes of Adele and Taylor Swift and Metallica and Chopin and Beethoven and God knows who else. Or, to put it one more way, that's equivalent to 5 million times the amount of stories that was offered on the Apple Lisa that Wayne helped create back in 1983. So, why do we need all this computing power and all this data when these guys got to the moon and back on little more than, well, it was diddly squat in comparison to what we use these days? Well, the reason is as follows. They were concerned with telemetry and guidance so they could get up there and get back safely. We do a whole lot more than that. And that's what Eric's going to tell you about now.
Yeah, so we actually have quite a lot of code, software code at LCO that we've written ourselves, about 1 million lines of code. And we actually have millions more that we use that other people have developed in open source communities, and we leverage that to build our stuff.
Yeah. So is 1 million lines of code a lot, Eric? Or?
Well, that's a good question, Brian. It's more than the space shuttle. The space shuttle is about 500,000 lines of code. On the other hand, it's substantially less than Windows Vista Ultimate.
Oh, yeah. One of the
is-
best operating systems ever.
Which is 50 million lines of code. So it all depends on your perspective. But here's another way of thinking about it. If you turn all that code into text and put it in a book, you would get 14 copies of War and Peace. Now, we have a software team of about 7 people. So that means each person has to understand 2 books of software distinctly. And then they have to work on that stuff and figure out how to edit that and improve it and add to it and so on. So yeah, I think it's actually quite a lot.
So, what does all this software do?
Well, we use it to operate our motors and our cameras and our pointing so that we can point in the right place in the sky. In fact, our pointing is so accurate that we can point at something the size of a penny from a kilometer away. And we use the software to monitor everything because there's nobody there at these telescopes. We need to know what's going on. Thousands of pieces of telemetry are coming back to us every day. And we can monitor everything from the weather and the humidity to motors that are traveling at hundreds of
Times a
hertz.
second.
Times a second, yeah.
Ah. Can we monitor North Korea? No, perhaps not.
Okay, so what's it all for? Well, this is Tabby's star. You heard about Tabby's star in the break. You might say to LCO, get me a picture of Tabby's star, please, sometime in the next 2 days. And then that's what we'll do. We have the web app that we wrote ourselves that you can log into and ask that question. And then we'll put it in with everybody else. Now, the thing is, there's a lot of stuff that we're trying to do. At any given time, there are around 10,000 requests in the scheduler being considered for observation. And so you have to compete with everybody else. We have to figure out when your stuff rises and sets at every site that we have. And then we have to figure out how important your stuff is and how urgent it is and whether we should do it or not. And then we make a schedule. And if anything changes, we do it all again.
So, how does this schedule work?
Well, to give you an idea of the scale of this problem, imagine you're trying to host a birthday party for a friend. You ask your mutual friends if Saturday's okay. No, Bob can't make it. Okay, so you ask Bob when he is available. Bob says Tuesday or Thursday. Sarah's only available after 4 p.m. Ted can do 6 p.m. onwards, but only at the weekend. Frank can't do weekends. And Chloe can only do Friday, but on the other hand, she happens to be his wife, so you probably need to work with that. All right, so that's 5 friends. Now, add 9,995 more. And another dimension, you have a choice of 6 restaurants. One of them is vegan. All your friends have distinct preferences about the restaurants too. And you have to come up with this schedule within 15 minutes because all of these friends have other things they're going to do. And if you don't come up with a schedule, they're going to go do something else. And unsurprisingly, they're not all going to make the cut. I mean, how many friends can you fit in 6 restaurants? So you sit down with a pen and paper, you work frantically for 15 minutes, you split your 10,000 friends across the 6 restaurants, and somehow, miraculously, you produce a plan. You proudly hit send on your email, and then the phone rings, and it's one of the restaurants. They failed a sanitation inspection. It's it, the deal's off. You've got to do it again. That's 15 minutes in the life of the LCO scheduler. So, we've raced through a behind-the-scenes look at the observatory. We've discussed how a cutting-edge robotic observatory actually works and how telescopes all around the world are coordinated by a single master brain that treats the whole thing as a single instrument with many eyes. This tapestry of hardware and software is what underpins the awesome science that you hear about every month in Australia on Tap.
Yeah. Like, asteroids about to hit Earth? Don't worry, we've got it covered.
Cosmic explosions.
Hey. Planets orbiting faraway stars, no problem for LCO.
Alien megastructures that probably aren't real. So our job is to make all of these discoveries possible. We want to support the astronomers so that they can work on the really important stuff and so that you can find out more about how the universe works. Thank you.
Thank you very much.
Thank you very much. We'd like to remind you to send your questions right now to this phone number, 805-55-AOTSB, and we will answer them in a few seconds. So please send your questions in now. In the meantime, we would like to tell you about an upcoming event at LCO. So you may or may not know, June 30th is Asteroid Day. So we're going to be celebrating that at our observatory, and you're all welcome to come visit us. On Asteroid Day, you'll get a chance to hold a real piece of an asteroid that hit Earth, if you were not here last month at Astronomy on Tap. Get a chance to meet the engineers and the scientists who make everything that Brian and Eric told you possible. Tour our facility. We have some telescopes being built. We have some telescopes already that you can see in operation. And find out all about asteroids and our observatory June 30th. So there's more details at this URL, and please join us then. Okay, do we have any questions? Let's get Brian and Eric back up here.
Yes, come on back. You can't get away that easily. All right, so one question, and I believe this would be for Eric, is what is the cute scheduler called?
What is the cube scheduler called? Well, it does have a name. I feel like this might be a planted question. The name of the scheduler is Serral, which is a Welsh word, which means starry. I wonder who came up with that question.
I wonder. All right, remember, keep next questions over here. Next question, why North Korea?
Why not? Everybody likes Kim. He's crazy.
Will. All right. How was Santa Barbara chosen for the headquarters for LCO?
Well, Andy, I think you probably know this as much as anybody. I think a good part of this was, A, we've got the best weather in the whole of the world, and B, we were pretty close to UCSB, and we had a ton of there, and that really helped us kick forward during the early years.
All right, next question. Is LCO funded by North Korea?
No comment.
Ah. All right. Let's see here. And see some of these questions. You guys, come on.
Too rude?
Well, like some of these don't really work. Anybody else got any good questions out there? Because in real time, it is hard to pick the good ones out of the trolls here. Has Brian considered the effect of the magnetic field? I don't even know what that means.
Well, it's something to do with my magnetic personality.
Yes, must be. All right, I think since you guys aren't asking good questions, we will wrap that up. And remember, though, ask questions to people with a little star tag if you see us out and about here. And
Okay, it's time before we adjourn for the evening for our raffle. So you should have gotten a raffle ticket when you came in. Please take it out now. We're going to be raffling the universe-famous Astronomy on Tap beer glasses. So you can have your own one of those. So, and can we get Sally back on stage here to pick our winner? We're going to be raffling out 4 of these. So each one of our speakers, and Andy is going to be picking one. So have your raffle ticket out. Take a look at the number. Here we go.
number is 039596.
596. If your number is called, come up stage so we can give you your beer glass and make a noise so we know you're here, or we'll give it to someone else. 596. If you're here, make a noise and come up, or we're going to do this for someone else. Is 596 here? I'm guessing not, so let's do another one.
584.
584, are you here? Make 584. Is 584 here? Nope. Okay, we're giving your glass away.
All right, let's try again. 514.
514, are you here? Yes. Okay. Congratulations. Okay. Next one. Pick a good one here.
I'm going to pick a good one. This is going to be like the Powerball. Okay. Right. 581.
Is 581 here? It is. Are you? Yes? Make a noise. Let us know. Come up. 581, was it? 581. Are you here? Doesn't look like it. Okay. Wait. Who? No. 585 is not 581.
Okay. 607.
607. Are you here? 607. Come on. No 607. Okay.
Okay.
Where are all these people?
539.
Yeah, not 539. Okay, who is 539 here? 539. Apparently not. Okay, we're going to keep trying.
Okay, I'm going to try and pull 538 if that was the one. No. Okay. We have 585. Come on.
Is 585 here? Yes, come up. 585. There you go. Thanks. Okay, two more.
Now, remember, in your LCO pint glass, there will be at least one wimp every time you drink out of it. So it's a good thing to have at home. And it's a good fact to know to tell your guests. 550.
550? Oh, okay, come down.
See, that's how it's done, boys. You just, I'm telling you. I don't know why.
Okay, we're going to keep 550 here until they get down and do the next one.
$593.
Yes, 593. Well done. Are you here? Come on up. We have 550. And the last one, which was 593. Oh, you're 593. Okay, 550. Here we are. Good luck. Good luck with that. Yes. Okay, we might be able to help you with that. Okay, we'd like to thank all of our speakers today again. We'd like to tell you that our next event is going to be on July 12th, and we'd like to ask you to go to this URL or scan this code to fill out a short survey just telling us, you know, who are you and why do you come to Astronomy on Tap, because we really don't know. And that will really help us out. So please take 5 minutes to help us out with our survey. All of our events are on YouTube, or follow us on Facebook and Twitter, and thank you very much for coming tonight.